I think we both agree there are many logic systems. Each of them is designed for something and also is good for something. There's many more to come, that's for sure. I think there is I don't know whether you agree with me, but I make a strong point in my talk that I think there is a major difference we need to stress. That is, that's also the topic of my slide. I don't think to use mathematical logic as the logic of everyday thinking. I think there is a major mismatch between the two. Mathematical logic will indeed give us a lot of things to learn from, a lot of things for us to inherit. But it's a stress that I think that's the assumption about knowledge and resource. I think that's a big thing. I don't know whether you agree with me or you just think, what I propose is just kind of like just another logic. It's basically the same thing as before, or it's really that different. What's your comment?
For me, mathematical logic is indicated by everything that I'm now circumscribing, by definition and nothing more. Although control strategies, data structures, and algorithms applied to that, technically speaking, is here in the case of some entries and not here in the case of others. But if we have Prolog, then, and we have some of the content in Prolog that relates to, say, classical mathematics, which is entirely possible, then that failing here, but then that would be, for me, still in that space. So everything else is outside of mathematical logic, and the key distinction historically, as I look at things, is between extensional logic and intentional logic. Everything in the domain of mathematical logic is merely extensional because there are no psychological attitudes directly modeled by the logic. So I don't think we fundamentally disagree about the limitations of mathematical logic. And the sad fact is, for whatever reason, AI got off on the wrong foot. It got off on the foot of focusing, and still by our textbooks still does, focusing on extensional logic, and specifically the part of extensional logic that originally pertained to how do you formalize what is a proof in mathematics. Starting with Aristotle all the way through to at least Frege, that was the driving concern.
Yeah, so we agree on that one. The related question is, what's your attitude toward model theoretic semantics?
Well, I think the two things you must know on the semantic side as a student in AI, if you intend on cultivating serious competence in logic, is standard model theory for extensional logic, and then possible world semantics. And I don't like possible world semantics at all for doing things on the side of human cognition in AI. I don't like it whatsoever. Even in the case of epistemic logics up here, I think it's pretty easy to show why possible world semantics don't work. You have to be careful because this is politically, I don't, but students would have to be. You have to be, because politically there's an entire part of logic-based AI that is driven by a model-based approach. This isn't like, this is literally models and possible worlds, specifically in the case of modal logics. There's a book called Reasoning About Knowledge that takes this approach. But it doesn't make any sense. So if I say that Pei knows that RU is located in Iceland, I'm not saying anything about your access to possible worlds. It doesn't make any sense. I'm saying probably that you at least believe it and that you have a justification. So it seems to me that your approach is actually much better aligned to take account of what knowledge and belief is than a possible worlds approach, which, by the way, was just appropriated historically because it worked for standard modal logic for possibility necessity. So, we latched onto it as expedient, but it doesn't make any sense to me. So I don't like, in particular, I recognize the power and importance of both of those directions in semantics, but I don't think they're satisfactory for doing AI work. Now, again, for a student, the student should know both before going on, I think, to what you're doing or other people doing things beyond them.
Agree.
Not before, I don't mean to be, but definitely should be included in their education. But that would be my claim anyway.
Okay, thank you.
Any questions on that or requests of clarification? Everyone knows what possible words logic is.
I don't, so.
Possible worlds semantics for, say, something being possible. If I said that it's possible that Chris drive a bicycle at 120 miles an hour unaided by any mechanical contrivance, that probably breaks physical law, but in modal logic, original modal logic, we would say that that is actually possible because it's mathematically possible. So the semantics that have traditionally been given for this add up to saying essentially as something along the lines of this. Well, things could have turned out differently so that Chris drive the bicycle like that if, say, before the Big Bang, certain parameters had been different, gravity had been different, what have you. There's some coherent description that seems, and that's all really possible world semantics ultimately boils down to. It gets a little tricky when we say things like it's possibly the case, that it's necessarily the case that something, and the relationships between the worlds are kind of weird. But that's basically the intuition. Whereas in the case of, again, Pei knowing something or you knowing something, it doesn't seem that it has anything to do with physical laws being different or mathematical laws being different or your accessibility or your accessing these worlds. I think we really just went down this route because the semantics for standard modal logic with possibility necessity was available and on the scene. Then we're like, okay, how do we get it up? Jaakko Hintikka still deserves a seminal, it's seminal work because he's the first who did that, but psychologically it makes no sense. Because again, psychologically, when we say that some human, cognitively anyway, knows something, presumably we're saying that they believe it, that they have a justification for it, and that it's true, because you can't know anything that's false. So those are the three traditional conditions for knowledge that are not reflected in the formal semantics, believe it or not, for epistemic logic. I tried to make some controversial claims. I'm glad to see everyone like me has doubts about evolution.
Well, I guess with that in mind, could you explain to us a little bit more about infantary logics and how they overcome completeness and consistency?
Right. There's one specific rule which, if allowed, permits the things which are not reachable by the axiom systems that Gödel talked about to be reachable, and that's this omega rule. What's going to appear on the lower right here is pretty much in terms of the basic ingredients that Pei mentioned, a specification of this particular logic. So I don't know if you can see it, but right here there's a label of R4, which says, this is simply by the label, this is the fourth inference rule that we allow. And we have a K, this is kind of juvenile. We've got a K, which is bolded, and we have an alpha, and then we have a T, and then we have a formula phi. And this is simply saying here that this agent alpha knows at this particular time T that phi holds. The rule tells us that we can infer that phi is the case, actually reflective of what we just inadvertently discussed in the exchange. So if an agent knows something at a time, then that thing is true. So in the case of the omega rule, there's something very, very remarkable happens. Above the line, we allow an infinite number of premises, but they have to follow the structure of ordinary mathematical induction on the natural numbers. So we would have to have phi 1, or better yet, if we were talking about the natural numbers, we'd have phi as a formula that would be capturing some assertion about 1, and then once again making the same assertion about the number 2, then about the number 3, and then 4, and then 5, and then 6, going on forever with 3 dots. The omega rule says if you have that above the line as a premise, then we'll allow you to make the inference that phi holds of every natural number n. That's the omega rule. And in many ways, what Gödel showed was that if you take the omega, if you don't allow the omega rule, then ordinary mathematics is incomplete. So that's one way of looking at it. And let me just say another way of looking at it is to say that he restricted his consideration of axiom sets to those which could be equivalent to what a Turing machine can do.
Well, that's exactly it. Because of what you just said, it
Yeah.
would not be computable.
Well, in light of what we're trying to do in our project, ultimately that is going to be the case. But there are some very surprising results about constructive versions of the omega rule, because the version I just gave is not a constructive version. It says nothing about having on hand algorithms for being able to compute phi 1, phi 2, phi 3, phi 4. Constructive versions say, all right, in the unrestricted thing it seems a little bit profligate. But if we really did have the algorithms on hand for doing each one, and we had an algorithm, a meta-algorithm that was able to supply the sub-algorithms each time a new natural number comes in, and we knew some of the desirable properties that we want to have for the meta-algorithm, then, can't you let us say that this will go through? And that really is what we're seeking to exploit in this work. But
Kind of the idea of what you were saying earlier about, you don't generate the formula from original conditions. You maintain almost a recognition of the pattern of that overall activity, and you can use it from that level.
that's right. That's a good way of putting the core of that. But still, ultimately, you are going to have to do some violence to the notion of representability in its modern. This restriction to Turing machine level axiom sets, the modern terminology is representability. And so you're going to have to do some violence to the concept of representability, which basically says, I want to have this axiom set at the level of Turing machines. So I don't want to mislead anyone. His theorems are theorems. They're proofs. It's not a matter of we have a little bit of evidence. But on the other hand, we know that he restricted his reference to axiom sets to those which are pretty simple compared to what human mathematicians consider. I mean, that much we know. I mean, because we know, for example, that the axioms for piano arithmetic, I flashed them up here, but now this slide becomes very relevant. I'm not sure where, I think is it here? So you say, well, how do I get this into a Turing machine or a conventional computer program? Well, you type these things in. They're finite strings, so they presumably could be typed into nars. That's not a problem. Everything times 0 is 0, the sixth axiom. But down here you have a little bit of a challenge, right? It says, and every sentence that is the universal closure of an instance of this is also going to count as an axiom. So this is an axiom schema. So actually, the number of piano axioms in the case of arithmetic aren't finite. It's an infinite set of axioms. But the infinity is tractable for a Turing machine, for a computer program, because you can write a program to do this, to generate each one of these in sequence, back to what we were just talking about with the omega rule. And here's the connection. So this is really just an assertion about if something holds of the number 0 and we then know the rule that if it holds of x, it holds of the successor of x, we can infer that it holds for every single natural number. This is really at heart the same issue we're talking about with the omega rule. And the universal closure just refers to the fact that if I have free variables occurring in phi, they all have to be picked up by universal quantifiers out here, so that's a well-behaved formula in first order logic. But it is infinite. It's just at the exact same size as the natural numbers, and in the case of the proof of Goodstein's theorem, that's actually just, that's the first ordinal number. So that's not sufficient to carry the proof through. But
This does seem to lend itself, though, to thinking that the concept of an infinite sort of logic, though, might lend itself, overcoming that problem lends itself to heuristics, the strategies, right? As we tend to do in solving most problems in machine learning, whatever you're working in, to overcome that problem, so it makes the problem tractable. And it ends up with non-optimal solutions, non-logistically optimal solutions. It ends up with solutions that are sometimes are going to fail. And thus, this is where logic tends to break.
well, I don't know.
If I may switch gears, because we've been on that subject we have limited time.
Sure.
There's a couple more questions that I'd like to get to. One is from Eric.
Yeah, I'm mostly concerned right now with methodological issues. It seems to me that, of course, one cannot expect to build AI that reach the level of human thinking, and then AI plus, and then AI plus plus, without the idea of self-construction at some point.
So, self-construction.
Yeah. We cannot ask a programmer to formalize the entire universe. I mean, then the intelligence is in the programmer's head, it's not in the system. So, at some point, the system, such a system, would have to have a clear modeling of its own operation. And I wonder, with such an approach focused on classical mathematical logic, what is the tractability when it comes from the system to model the operating system, the hardware is operating on, and the ways to improve, by ways, of course, of programming?
Yeah. Well, here's the slide that's perhaps, you said a lot more, but most closely related to the issues that you raise. And I think the first thing to notice is that, in fact, Deep Blue and Watson both are simply AI systems that reflect the ingenuity of the human programmers. But that's all we have so far in AI. And if there are any examples that if there are any impressive systems that can do more than those two, maybe of course in other domains, I would like to know them. So you're right, but so far we haven't been able to break out of that. I mean, what did Watson really do? I mean, Watson is fantastic, and I'm very good friends with the guy who led the project and have collaborated with him. Okay, so some brilliant people, some highly paid, brilliant people with a tremendous amount of incentives work together to create better and better, generally statistical algorithms for how to analyze text to correlate concepts and predicates that eventually correlated with the correct answer. This, as you say, would require more, because human intelligence does have this notion of self-improvement, self-construction, etc. Yeah, I don't know how to do that. because it seems to require creativity, and so I have no idea how to do that. And from my standpoint, this approach, your challenge to this approach could be embodied in saying, so great, so you created a new logic, and people just keep creating new logics, but if you're trying to model what you are, which is a person, what happened to the attempt to model the creation of a new logic? I mean, it's too hard. It's the hardest question of all. It's extreme creativity.
Right, but with a claim like this, HI is coming, then AI plus, how, knowing this hard question, what is your approach towards addressing it, since it must be answered at some point.
Well, anything with a finite space is barking up the wrong tree and might as well be thrown out, whether it's logic or machine learning or anything in problem solving. So that's all gone. Because this extreme form of problem solving is working in an infinite space of possible outcomes. With the guy that did, with Dave Ferrucci, we co-wrote a book on creativity, but it was all based on the engineering of trying to trick you into believing that the machine is creative. We say explicitly we don't have. I have no answer. I would love to say that I have another project idea or an idea for a new grant or a 5-year thing. No, I don't. I mean, I would try to go get funding for it if I knew how to do that. So I mean, and maybe other people can do it. I just have not. Those ideas have not congealed enough so that I would feel comfortable submitting a proposal for funding. In the case of Handel, the artificial conductor, okay, there is no raw generative power in Handel.
So essentially you're saying that you agree that in order to get AI plus and AI plus plus, we will need that sort of creativity, but we have no idea of how to do it.
Well, I didn't say that. I said I don't.
Ah, okay, yeah.
Yeah, there are other people who may be able to, figure that out. But up until, or at least with that one proviso, that's what I'm saying. Yeah.
Did you go, Joshua?
You started your talk with pointing out the shortcomings of the results that we got during the first 60 years of artificial intelligence. Now, that's not that surprising, otherwise we wouldn't be sitting here. And I think that we have been far longer working on the problem of understanding digestion. And we still don't know whether cholesterol is good for you or not. At least the opinion changes every 5 years or so. And it seems that there is no philosophy of digestion, and nobody is asking that we have to invent hyperchemistry before we can understand the problem of digestion fully, but we are somehow confident that we are going to work out the details somewhere in the future, and we have a rough understanding of the area where to look for. Now, you maintain this is completely different for the field of AI, and for some probably very good reasons. Okay. That is, we need hypercomputation in order to address some of the issues that we have failed so far, very specific issues in the history of artificial intelligence, namely consciousness, maybe creativity, and so on. So there are several kinds of ways we can achieve hypercomputation, things like closed time-lapse loops, that is, we can transport results of computations in the past, so we can use things that we are going to compute in the future, or we can use infinite precision real numbers, which contradict our current understanding of quantum mechanics and so on. And most physicists at this time don't think that hypercomputation is possible. Some philosophers like Copeland do. And the reason why so many people in computer science are uncomfortable with this is because if hypercomputation were possible, that is, we can physically build hypercomputers, it means that P equals NP. And as Scott Aronson has pointed out, this gives us some godlike powers. So a very reasonable course for us would be to adopt the position that P is not NP, because then either we are right or we have godlike powers. So either way, it's a good result for us. And if you argue for hypercomputation, it kind of implies that you think that P equals NP, and as a short Google search has told me, you actually do that, which is a very interesting point because it puts you into a very interesting position. And of course, this is not impossible, but at the moment, it's arguably a minority position. And I think to strengthen your argument, maybe you can expand on this, because we can not implement maybe such an algorithm on a computer of Turing degree 0, but of course we can specify it. We can specify a lot of things that we cannot compute with the Turing machine. And maybe you can specify those missing features, or at least some of them, like consciousness and so on, and other things in your upper right quadrant, and show exactly how you could solve them, address them, if you had hypercomputation available. Maybe this would help.
Okay. There's a lot there. The difference between the digestion case, to take that up first, because chronologically I think you began with that analogy, is that unlike, as far as I know, the science of digestion, the current gods of digestion, or the current gods of cholesterol analysis with an eye to whether you're going to die of a heart attack or not, depending on your diet, do not show up at their premier international conference sponsored by federal money from different countries and proclaim 6 months from now, we will have pinned down every aspect of the digestion system. In fact, we'll have personalized it to your genes, so just relax, give us another 6 months and we'll be done. But in the case of AI, we have a litany of examples of that happening. In fact, with the founders, and with the founders in connection with logic theorists saying, it's just a matter of time before human thinking and reasoning will be handled. And that's the major difference. I would say, secondly, there has to be some length of time, K years, after which progress on a well-defined scientific / engineering objective is going to be regarded as unsolvable. I mean, if we don't say there's some K for that, we're not doing science, we're doing religion. Then we're just believing this because we want to believe it. So you may be right, and I believe you are, that 2012 is not the year to throw in the towel and say something odd is going on here. But if we get to the year 3000, okay, the year 3000, it was 2000 for the Turing test. And for Hans Moravec, companies would be run by robots by, I think, 2020. He has 8 years. I wagered at that time my entire retirement package that his numbers would be off by a factor of half a century, okay? But he's wrong. He's got 8 years left. So the difference is we keep making these claims instead of saying what is wrong. Is it self? Is it creativity? Is it self? Whatever it is, something's possibly wrong. So that's the difference in my explanation for the difference between those two things. And by the way, your physician does make prescriptions in general without saying they figured the whole thing out. They're kind of like current AI people who are honest. You know, well, look, I can't build you a robot to eliminate human loss of life in Fukushima, but in the next generation, if you give me enough money, I'll minimize it by 30%. That's kind of like your physician saying, look, don't have steak every night. Your best bet is to be a little bit reasonable on the cholesterol, but we do have some good drugs now, so you don't have to totally eliminate cholesterol from your diet. And you hear that from physicians, probably even from researchers, although I don't know for sure. On the hypercomputation side and the P equals NP, well, I don't claim that in fact P equals NP. What I claim, and I could even be wrong about this, but what I claim is that if two things are assumed, then we can put together a formal argument. And for me, a formal argument is no different than a proof, because a formal argument still has to be verified step by step, but the premises may be suspect. But there's no difference. The two things we need are Wolfram's picture of the universe to be true, that the universe physically is nothing more than a massive Turing machine with sub-Turing machines with sub-Turing machines. And then in modal logic, in quantified modal logic, the Barkin formula has to be true. And most logicians do not accept the Barkin formula. I'm in the extreme. There's Edward Zalta at Stanford who accepts the Barkin formula, which basically says you can infer to the overall necessity of something if you can find out that something's seemingly necessary in our world. So I only claim that I have an argument for it. I don't think P equals NP if I had to wager on it. But if we have a proof that P does not equal NP, and this is not independent, say, of set theory, then as I say in that paper, which hasn't been published yet, we would have, in some sense, a conflict. So we'd either have, if my reasoning's correct, we'd either have to give up Wolfram's view of the universe, which many people are prepared to do anyway. We'd either have to give up that, or we'd have to give up the Barkin formula. And what every logician's going to say is, well, sure, I told you so about the Barkin formula. So that's, you know, my attitude about that. But in terms of hypercomputation, now there I have to disagree with you, because we should be able to prove that hypercomputation is, if it's physically possible, we should be able to prove that it is, and this should not be something like we're waiting for 5 centuries from now. And the reason we should be able to do that is we can now be reasonably certain that we've axiomatized parts of physics. It's primarily, there's a group in Hungary that tends to focus on this at the Renier Institute of Mathematics in Hungary. There's a candidate formalization for quantum mechanics and then for special in general. So therefore, we should be able to do a consistency proof, theoretically, for time travel. And so if in fact, which you mentioned, if in fact we have a coherent, it can't just be a story, it has to be expressible in the formalization for how, if you could travel through time, solve the halting problem. Then, it's not like we want to prove that we can build it. We first want to just be able to prove that this is mathematically possible. And that we should be able to do. Nesmeti, who is probably the foremost authority in the world on the intersection of physics, mathematical physics and formal logic, I mean, he does believe that I mean, not only does he quote, knows that's possible, but he believes that hypercomputation is entirely possible because of what he suspects about this result. And you'd say, well, he's not a physicist, he's more of a mathematician or a logician. Well, sometimes when you get to the only physics I understand is mathematical physics. I don't know nothing about the physical world. So I don't know. I don't know what you want to say about that one. But finally, I would say that you're conflating harnessing hypercomputation with hypercomputation. So we've known since Porel and Richards wrote a couple of papers on physics and hypercomputation that from the modeling perspective, hypercomputation is there. We just don't know whether those models are accurate descriptions of the physical world. But even if you took the additional step and said, yes, those models are accurate and there are hypercomputers in the physical universe, our ability to harness them would be a completely separate endeavor. And I don't know that we would be able to do that. I mean, I don't know. Seems unlikely. My view in the case of what we do is that we actually don't consciously harness most of the problem solving that we do. We consciously labor to follow the heuristics and the craft of what it takes to be an accomplished problem solver in whatever domain we're in. And then we don't know how we get the answers, but the answers come to us. If we knew how the answers came to us, we would just turn everybody into being much smarter. But we don't know how to do that. So my view is the reason we're so darn smart is that in the background, unconsciously, there's amazing problem solving happening, and I suspect that it's hypercomputation. But we can't consciously harness it for any one particular thing or other. How does Cantor come up with a brand new class of numbers in the? I mean, if you ask me, I don't know. I was playing around and thinking about, and I posed this question and I posed that question, and then it came to me. All right, well, that's not very helpful for trying to mechanize intelligence.
For those not familiar with hypercomputation, could you give a quick summary?
Sure, I'll give a quick summary and I'll give a quick pointer to a starting paper, because if you're familiar with Turing machines, well, who's not familiar with the Turing machine? Okay, good. Well then, the second thing first, there's a good paper in the Journal of Symbolic Logic called, I think it's just called Infinite Time Turing Machines. So it gives a definition of Turing machines able to do an infinite amount of work in a finite amount of time. And then on the first point, that's people will deny that, and you're probably aware. I mean, people deny that that's. I mean, at least I'm not that bad. That every time I see a hypercomputer, regardless of what format it is, somehow someone's sneaking in the concept of doing an infinite amount of work in a finite amount of time. So the virtue of infinite time Turing machines is that the announcement comes right out there and is explicit. It's an infinite time Turing machine. So if a Turing machine could, this is the traditional entree, if it could take half the time it took for its previous operation in its current one, and then half the time again, it could solve the halting problem because it can enumerate all of the natural numbers in a short amount of time, like a second or 2 seconds. First operation is half a second. Next operation is quarter, right? We just keep going. And so one entree to hypercomputation intuitively is take that notion of ever faster and more, in each one of the steps, and then formalize it. I mean, isn't that partially why the calculus, why elementary differential and integral calculus is an answer to Zeno's paradox? It's actually already buried in the concept of a limit. And so the other historical entree to hypercomputation, they didn't call it hypercomputers. Yes, that's Jack Copeland's name, but this has been around for a long time. It was Weil, the mathematician Weil. It was Bertrand Russell who first talked about this speed up. Russell, for example, thought it was mathematically possible to have and Weil to have a device that would work ever faster. But in the case of a limit-based approach, there's the original definition of what computational learning theory meant. And originally, computational learning theory was all based in traditional theoretical computer science, recursion theory. And there the idea is computing in a limit. And all that meant was just what I said, that you can compute the halting problem and equivalent problems in the limit because you get faster and faster. And they added the concession that didn't mean you would have to know the answer was correct from the machine that was doing this processing. All that mattered was that you knew in general that the machine would only change its mind a finite number of times in an infinite progression. And the second edition of the book on computational learning theory is out there. I forget what it's called, but it goes into coverage of these formalisms being relevant to their theory of science. The way they model what a scientist does essentially makes use of hypercomputation. And that's been going on way before. I don't even think Copeland was born. I don't know how old he is, but I don't think he was born then. That appeared in the first two papers, seminal papers by Gold and Putnam. I think maybe Hillary Putnam is still alive. And that was 1960.
Josh, does this actually...
It doesn't entirely address the core of my question, no.
Okay.
Let me rephrase the question very briefly and maybe much more provocatively.
Okay.
So let's say I don't understand how thinking works. A lot of people have been putting serious effort in it, very smart people. So I suspect we need something new in the equation to understand it, and maybe it's fairies. Now, of course, I can axiomatize fairies, so there's nothing wrong with that. I know some extremely highly paid and very smart people who believe in fairies, even though the majority doesn't. So we get this out of the way. Fairies are a possibility. Now, what remains, and this is what I would like to ask you, is to elucidate how exactly the fairies are pulling this off. How does the hypercomputation help you to achieve consciousness? The argument that you gave in the beginning as an answer means the opposite, because if the AI people didn't do this by conventional means in just 60 years, it doesn't prove anything with respect to the existence of a novel idea with fairies and so on. You should give some evidence on, or you cannot, because we can show that this is not classical physics or not Turing machines, so the current approaches are doomed. We need something new. But you should at least show how the new approach is going to enable this beyond saying, I have a suspicion that this is what goes on behind the screen somewhere.
Right. Well, first, I didn't say that hypercomputation is the answer to the consciousness riddle or the consciousness problem. I'm saying the opposite, okay? You have three contributors in terms of a type of, if you will, cognition or mentality. You got a contribution from this, and a contribution from this, and a contribution from this, okay? And so, though I said this box is the set of all functions from natural numbers to natural numbers, and therefore comprises the traditional relevant space for computability theory. You know, there's a lot more to math than that. But at any rate, this, and I continue in both directions, this includes everything that is expressible in a third-person formal scheme. So we'll include set theory, where we introduce the theory of ordinal numbers down to, you know, basic Turing machines in your first class. This box over here includes phenomena that you can't capture in a third-person scheme, in particular in a mathematical third-person scheme. So I think a lot of what we do that makes us us is going to be forever inaccessible to anyone who's restricting themselves to third-person formal schemes. And we don't have time to, so what contribution does that make to human intelligence? Because it doesn't follow that even if you're right, Selmer, that we can't do an end around and do it in another way if you don't tell us what it's good for. Well, that may be true, but the first point is I'm saying the opposite of what you're saying in terms of the breakdown. In terms of things that we do in here, I would say that anything that's creative and leverages our capacity to feel, to have raw feelings of consciousness, would be something that would be in that category. So the ability to write a great novel would leverage your capacity to put yourself in the shoes of your character, and you can't do that without being conscious as far as we know. Now, here's the hypercomputation space, and this is generally, it's suggestive but generally accurate, right? Because in terms of the functions that are Turing computable in this space, this line ought to move down to here. You know, I remember having a debate with Marvin Minsky about this. I noticed that we never had another debate. I drew this box and said, Marvin, every point up here is not Turing computable. And the line goes across here. And every point below the line is Turing computable. Now you want me to believe that we've mathematized this and we understand it. But let me get this straight. You wanted me to believe that human cognition is constrained to this little part up here, even though this is completely coherent, and this was a long time ago. Now the math gets robust by the month, more robust by the month. If anyone has the burden of proof on them, it ain't me. It ain't me. Someone has to give me an argument for why, though I can chart this terrain up here, do theorems galore about it and understand it, I nonetheless have to be restricted as an information processor here. Why in the world would we ever start with that assumption? You know why? Because these things the things that are like this happen to be things we can build to make money. We can, you know, break the Enigma code in World War II. DARPA can get a speech recognition system that Apple can end up buying for $200 million to make themselves a fortune. All of this is what we can work with, and we focus on it, and what happened to all of this? I know, I don't have the burden of proof on me. I'm sorry, I reject the premise.
To more mundane pursuits.
Okay.
You had a program that you maintained is conscious of itself.
In a limited sense.
Yes, in a limited sense.
Remember, what it can do in terms of all I'm saying I can do as a funded AI engineer is you give me the test, and then I use my techniques to build the artifact that passes the test. In that case, the test is the mirror test for self-consciousness.
So basically the sorts of things that it can't be conscious of is they are enumerable. Because you design it to pass the test.
I designed it to pass the test, that's right. And you mean the things it will fail on that are other tests of self-consciousness? The other tests of self-consciousness will trip it up and it will fail.
Yeah.
Oh, absolutely. Absolutely. And this very much related, believe it or not, relates to what I was just saying. But that's not how contracting works, at least in the United States. You're an agency, you contract for AI work with me. If you say to me, I needed to work in the infinite space, no one's going to, if they take that money, the statement of work is going to list that at the very bottom as something which they'll give thought to. They will never be able to deliver on that. And I can't deliver on it.
I actually had a suggestion.
Okay,
on
good.
it.
Yeah. Yeah.
Isn't this a prime example where a feedback loop would actually help you?
Suitably interpreted, the phrase feedback loop would definitely help me. Now, my interpretation there, and it's something that I would love to pursue, is we have to generalize in some self-improvement scheme from what Cogito is able to do with the mirror and this red dot. We have to look for the attributes that are more general in the environment that Cogito perceives and a more general conception of his body. Okay, and in fact, that's defense, that's just actually ultimately defense work. Because the driving desire is that when robots are in a battlefield, two robots, and one robot raises its arm, okay, the robot next to it has to realize that's not my arm. Or if it is this robot here, it has to realize, oops, that is my arm, and whether it should operate with it. But you're right. I mean, that kind of direction should work. But remember how limited how unimaginative I am in my techniques, right? So the feedback loop has to be cashed out in keeping with the only kinds of techniques I understand, but yeah.
It seems to me like when you take this approach where you are actually given some tests, it could be IQ tests or whatever tests,
right.
Self-consciousness tests,
right.
And you then pursue to build a machine that can pass the test, it feels like to me like a friend of mine who wanted to find all the psychological tests out there to train their kids on them so that they would pass them.
Right.
And and that's, everyone knows that's cheating. So to me, it seems like, if you're really seriously interested in AGI, we should be looking for something below that threshold, i.e. a general mechanism that can actually evolve or learn to actually pass those tests without us engineers, building specifically solutions to pass the tests.
Yes. No, I couldn't agree more. In a book that Pei is the editor of, and got good feedback from Pei and others, there's a version of that explored where you constrain the test, which happens over here, to the agent waiting here at the machine. You have your objects over here, and they have known purposes. And this is all the agent gets exposed to first before being presented with a test out of the blue. And I will go that far that, that seems like something I could attack. But if you're going to say that, look, you're cheating even here because you have these objects and you know their purposes in each case, general purposes, if you're going to tell me that you're taking those away from me, which is to say that you're erasing this. You are right. That is much more sensible as an ultimate objective for AGI, but as I confessed earlier in the discussion about self-improvement, I don't know how to do that. May relate, for starters, to the fact that logic starts right off the bat with a symbol set. So wouldn't we have to come up with symbol sets by learning, either innate learning or non-magical learning? So yeah, I mean, you're exactly right. That would be the way to go. Yeah. I would repeat. I don't know how it is in Europe and in the and like say in the EU, but for funding, I mean, there's a tension here with AGI, is that we know that AGI is asking the toughest questions. We know that AGI is the most, scientifically speaking, it's the most sensible approach to AI. It really is. And the most honest. But on the other side of the coin, we have the fact that there's not a whole heck of a lot of money available. There is, but you're working on it, so you have to scale up somehow, because it's not directly available.
Yeah, no, that's actually a really valid question and an interesting one, and we'll spend some time on that in the coming days on methodology. But we have a question here.
Yeah, just a quick question. You mentioned Barcelow's simulation theory.
Yeah.
I'm interested in your take on this simulation stance. For example, in its relation to what we're talking about here and your architecture, and your particular take. And you mentioned also this CNN test for theory of mind. It's usually also modeled using this simulation-based approaches. So I'm putting myself in your shoes, for example, this kind of stuff. So I'm just interested in your take on this stance.
Well, I didn't catch the last part, so I'll have to re-ask you about that. But Barzilai and who's the guy? It's a philosopher of science connection. Not Churchland. He's in Canada. Shoot, I don't remember. But Barzilai, these two guys came the 2 successive weeks to RPI to give talks. And so in both cases, I asked them about infinitary reasoning and infinitary structures. And in both cases, they said, Barzilai said, I think I can begin to see how you could abstract somehow from a simulation to omega and ordinal numbers, but I'm really not sure how. Then I talked to him a little bit later, and he said, I don't know how. So, see, this is the first problem, is that the very things that I'm working on now are things which are only promissory notes in the simulationist approach. Because the vocabulary of many of the things I'm working on, the first class vocabulary referred to objects which seem so abstract from the standpoint of a simulation, particularly any kind of sensory-based simulation, that doesn't seem to be a way to bridge the gap. And it wasn't Churchland, but he's always suitably dismissive of in his case. I said, well, what about omega? What about Aleph naught and things like that? I don't see how they would even be possible to express in your system. And he said, well, only like 0.3% of the population is concerned about that anyway, so I'm not concerned. So that was dismissed. So, I don't know.
From the practical point of view, do you think there are useful theories?
From the practical point of view, I think for some tasks they could be extremely useful. For example, if you wanted to build a synthetic character in a computer game to interact with ways that might be very attractive financially to people to buy, a simulationist approach might make a lot of sense. That a simulationist approach might explain animal level cognition to a high degree. How it explains our capacity for higher level cognition in mathematics remains to be seen, but it doesn't look like on the face of it can. And I suspect that's part of their research program going into the future, is to try to explain how to do that.
Could you maybe combine different theories? Do you think it's feasible?
I do, depending on the project, think that might be a good idea. In the case of epistemic logic, the simulationists are direct competitors, because the people doing epistemic logic say that when I develop a model of what you believe about me, okay, that's best modeled by looking at the formulas that I believe, okay, that in fact you believe about me. Simulationist says, look, it's not symbolic, certainly not at that level. It's actual, we interact. Now there's a mental counterpart to that interaction that's happening in here. So forget about this fancy symbolic information. There have been some harmonization. these are you know, competing things in the human sphere. Now in the animal sphere, you know, and I'm on record as saying I didn't think dogs or whatever could do fifth order beliefs. I don't think they can do third order beliefs. So maybe they are instinctively somehow drawing on repetitive interaction that they have had with relevant stimuli in the environment, and they have that in their head. I don't know. In Darwin's Descent of Man, he talks all about dogs' canine problem solving and says it's fundamentally similar to human problem solving. So he gives the case of dogs on thin ice. Well, dogs going onto ice, they realize it's thin and they quickly get off. But that there looks like it's probably simulationist memory instinct rather than, gee, golly gee. I've never been on ice before, but I do recall the phenomenon of gravity effect, you know.
On that note, let's give Selmer a big hand.